Hi everyone, I'm Wei Chow from ByteDance and the National University of Singapore. Today I'll present our CVPR 2026 paper, EditMGT, Unleashing Potentials of Masked Generative Transformers in Image Editing. This is joint work with collaborators at ByteDance, NUS, Shanghai Jiao Tong University, and HKUST Guangzhou. Image editing today is dominated by diffusion models. They produce stunning visuals, but they share a fundamental flaw. Their global denoising process leaks edits into regions that should stay unchanged. Ask the model to recolor a hat, and the background often drifts too. We call this the spurious edit leakage problem. Prior work tries three things. 1. Train on more high-quality data and hope the model learns to behave. 2. Use predefined masks together with an inpainting backbone, but flexibility suffers. 3. Invert the image to noise and remap, which is slow and still leaks. None of these explicitly guarantees preservation. We need a fundamentally different decoder. Our insight is to switch generative families. Instead of diffusion, we turn to masked generative transformers, or MGTs. Unlike diffusion, an MGT predicts masked tokens in parallel. Generation is local at the token level, giving us efficient inference, plus explicit control over which regions get modified. To turn this into a real editor, we need two capabilities. First, adaptive localization. Figure out where the edit should land without a user-drawn mask. Second, explicit preservation. Guarantee that everything outside that region stays untouched. For the architecture, we feed the original image as a second token stream CV, mirroring the editing stream CI. They share weights, but CV's timestep is frozen at 0. The streams interact through an attention bias controlled by a scalar gamma. 0 ignores the source. Greater than 1 strengthens it. This turns a text-to-image MGT into an editor with 0 new parameters. The cross-attention maps of MGTs already carry localization signal, but raw maps are noisy. We aggregate attention from blocks 28 through 36 to amplify the signal, then apply adaptive filtering to sharpen boundaries and fill internal gaps. The result is a clean, semantically aligned localization map. When the prompt says hat, the map lights up the hat region. The inference trick, region hold sampling. From the consolidated attention, we compute a localization score S_L per token. Tokens below threshold lambda revert to the original. Tokens above flip per MGT schedule. This keeps editing strictly inside the relevant region. Lambda is the single intuitive knob. Higher means more conservative. High-resolution editing data is scarce, so we built Crisp Edit 2M, 2 million samples across 7 categories, every image with short edge at least 1024 pixels, all generated using strong open-source models with rigorous filtering. Combined with 2 million additional samples we collected, the total training set reaches 4 million pairs. Training proceeds in 3 stages. Stage 1. Replace clip with Gemma 2 billion as the text encoder, aligning on 1 million image text pairs for 5,000 steps. Stage 2. Full edit tune on 4 million pairs for 50,000 steps. Stage 3. 1,000-step polish on the highest quality subset. Across 4 benchmarks, EMU Edit, Magic Brush, AnyBench, and Gedit, EditMGT sets state-of-the-art on image similarity. On AnyBench, 3.6% gain on style change, 1.7% on implicit instructions. On Gedit, despite only 960 million parameters, we match the 12 billion flux context model overall, and beat it by 17.6% on style transfer and 9.8% on color alteration. And we do this 6 times faster than comparable methods, about 2 seconds per 1024 by 1024 edit, with just 13.8 gigabytes of memory. Qualitatively, EditMGT understands instructions like looks a bit yellowish, the way a human would. Code, dataset, and project page at ycow23.github.io/editmgt. Thank you.